It's kind of like when you show a friend a drawing for just a split second and then you ask them to redraw it from memory. Their version isn't going to be a perfect copy, right? But it'll capture the essence of the original. Well, what if a machine could do the exact same thing? Today, we're going to pull back the curtain on the autoencoder, a really cool type of neural network that literally learns to see and then redraw the world around it. Let's dive in.
So, our whole journey today starts with a little bit of a mystery. We've got a machine, and its job seems pretty simple on the surface. Just redraw what it sees. But, as you're about to find out, what's happening under the hood is way more interesting than just playing Toppy-K. Okay, take a look at this. On the top row, you've got a bunch of original handwritten digits. Simple enough. But look at the row below it. That's the machine's attempt at redrawing them, purely from memory. You'll notice they aren't perfect photocopies. They're a little fuzzier, maybe a bit softer, but the core idea of each number, it's captured perfectly. This is reconstruction, not just replication, and that right there is the key difference. And that really brings us to the big question, the main event of this whole explainer. How on earth does a machine learn to do this? How does it look at a grid of hundreds of individual pixels and somehow grasp the fundamental idea of a 7 or a 2?
Well, the answer lies in this really elegant piece of tech called an autoencoder. So let's do it. Let's pull up the blueprints and see exactly how this learning machine is put together.
So what is an autoencoder? Well, at its heart, it's a neural network that's designed to do one thing and do it incredibly well: redraw whatever you show it. And the way it gets so good is by mastering two skills. First, it has to learn how to compress all that data into a super short, efficient summary. And then, it has to learn how to uncompress that summary back into the original image. It's a game of compression and reconstruction. This whole process really breaks down into a two-part job. First up, you've got the encoder. Think of it like an expert summarizer. It looks at the whole image and boils it down to just its most critical information, a short, essential code. Then you have the decoder, which acts more like an artist. It takes that tiny little code as its only clue and tries to redraw the entire original image completely from scratch.
Okay, so we've got the concept down. Now let's get our hands dirty and see how this thing is actually built. We're going to look at the architectural blueprints, the actual core logic that makes this machine tick.
This here is the encoder's job. Now, don't worry about the specific code, just focus on the flow, on the funnel. We start with 784 pixels. That's our 28 by 28 pixel image flattened out. The first layer squishes that down to 100 features, and the next layer squeezes it even tighter, down to a dense little code of just 30 numbers. I mean, think about that for a second. The entire visual identity of a number is being forced into a summary that's more than 96% smaller than the original. This aggressive compression is what forces it to learn what's important.
And then, on the flip side, we have the decoder. And, you guessed it, it does the exact opposite. It takes that tiny 30-number code and uses it like a seed. It expands it back up to 100 features, and then from there, it reconstructs all 784 pixels to draw the final image. It's this perfect, symmetrical mirror image of the encoder's job.
Finally, with just one simple line, you snap the two halves together to create the complete autoencoder. An image goes in one end, gets compressed by the encoder, that code gets passed to the decoder, and the new, reconstructed image comes out the other end. It's just a really beautiful and elegant design. But, building the machine is only half the battle. A freshly built autoencoder is basically an empty shell. It doesn't know anything. It has to be trained. It has to learn how to see, how to summarize, and how to redraw effectively.
So how does it learn? Well, it has a teacher, and this teacher is called a loss function. A better way to think of it is as an art critic. After every single attempt the machine makes to redraw a number, this loss function compares the machine's drawing to the original and calculates an error score. A high score means, nope, that's a bad drawing. A low score means, hey, you're getting really close. The machine's entire goal during training is to do whatever it can to get that error score as low as possible.
And this is where that training happens. This fit command. It's basically like telling the machine, all right, time to go to the gym. We give it our huge data set of images, and we tell it to practice on the whole set 10 times. Each one of those full practice runs is called an epoch. And during every epoch, it's redrawing thousands of images, getting feedback from its art critic, and making tiny little adjustments to get better for the next try.
And you can literally see it learning right here in this graph. The vertical axis is that error score, the loss, so lower is better. And the horizontal axis shows the 10 practice rounds, or epochs.
Just look at how that blue line, which is the training loss, absolutely plummets after the very first round and just keeps getting steadily better. This isn't just a line on a chart. This is visual proof that the machine is genuinely getting smarter.
All right, so we've built the machine, we've put it through its training montage. Now it's time for the big reveal. Let's see the final results of all that hard work.
And so here we are, right back where we started. But it's not a mystery anymore, is it? Now you know exactly what's going on behind the scenes. An encoder squeezed each of those numbers down to its 30-value essence, and then a decoder used that essence to redraw the image from its memory. It isn't magic. It's just the really cool result of a well-designed, trainable process.
So here's the big takeaway from all this. By forcing a network to squeeze information down and then build it back up, we actually compel it to learn the really meaningful underlying patterns in the data. We've seen it work with simple numbers, which it really just leaves us with a pretty powerful question, right? If a machine can learn the essence of a 7, what's stopping it from learning the essence of a human face, or a piece of music, or even complex human language? The possibilities are just vast, and it all starts with this simple act of learning to see.